I will share my screen. Can you see my screen?
Yes, it's perfect.
Okay. Okay, so good morning, everyone. My name is Gilberto Berardinelli from Aalborg University in Denmark. It is my pleasure to welcome you at this webinar on sustainable wireless design. So this webinar is a joint effort of the 6G Shine, Super IoT, and the Terrameta SNS projects. So why this webinar? In our research on 6G, we are dealing with very demanding performance targets in terms of data rate, latency, and reliability, and so forth. And achieving those targets requires the usage of very advanced communication technologies and very high frequency bands. There is therefore the obvious concern that the usage of these technologies might not be sustainable, especially in terms of energy consumption. It is therefore our task as researchers and engineers to design a 6G and deal with advanced technologies in a way that they can be made sustainable, while at the same time being able to achieve very demanding communication requirements. So today we have 3 presentations that are addressing the design of complex technologies while considering their sustainable implementation. The first presentation will be given by Luis Pessoa from INESC, and the presentation deals with sustainability of reconfigurable intelligent surface-based networks. The second presentation will be given by Meng Li from IMEC, and the presentation is focused on the sub-terahertz transceiver architecture power analysis for extended reality indoor gaming scenarios. And finally, the third presentation will be given by Yasser Karagoes from KU Leuven, and the title of the presentation is Biased FSK Modulation for Efficient SWIFT in Sustainable IoT Systems. So after each of the presentation, we'll give, of course, the floor we open the floor for comments and questions by the audience. I think that's pretty much all from my side. I can stop sharing and leave the floor to the first presenter. So Luis, if you'd like to start with your presentation.
Sure. Let me share my screen. Right, so I have it in full screen already, and you should be hearing me.
Yes,
well.
Yes, it is fine, yes.
Okay, so I will start now. So thank you very much for this organization of this joint webinar. I'm Luis Pessoa from INESC in Portugal. So we are a research institute, and myself, I am the coordinator of the SNS Terrameta project. But I'm also a participant in the Super IoT project, and some of the work that I'll present is also involved in Super IoT. So this is a nice joint work between these 2 projects. So let me start with the motivation for this work that I'll be presenting today. So basically, the driving forces for 6G, and you might have seen this figure before, are related with sensing. Is a very key feature for 6G in order to address several requirements, such as in autonomous mobility, industrial automation, robotics, digital twinning, XR. You will hear today about XR in our presentation. There is a trend in migration from performance to values, so from KPIs to KVIs. So you will hear a lot in the coming years more and more about KVI. So this is about the value that is provided to the society and to the mankind, in economic, societal, and environmental values. And in this way, sustainability is one of the overarching thematics for 6G. You see there are 4 overarching thematics here around. Sustainability is one of them. And sustainability also has these same 3 dimensions, economic, so we can think about cost, societal, impact on the society, and then environmental, when we think about life cycle assessment and things like this. So my presentation is mainly about reconfigurable intelligent surfaces. Also, this is, let's say, the hot keyword, but you might hear about reconfigurable antenna arrays from several years ago, and these are important in cellular communications, mainly to provide high terminal density, because with the antenna array you are able to focus the radiation into more directed beams in order to provide higher data rates to each individual terminal or user. It is also supporting localization and sensing, such as kind of radar sensing. In the state of the art, there are these phased array technologies that, let's say, are current and common technologies implemented on base stations. Also, not only let's say cellular base stations, but also for example satellite ground stations and so on. So this phased array technology is completely mainstream. However, it has several problems in terms of sustainability, I would say, because it requires multiple transceivers inside the antenna, and it's will have high power consumption, among other problems, such as difficult to scale in size and the bandwidth. In this sense, reconfigurable antenna arrays, and when we say reconfigurable antenna arrays, we are talking about spatially fed arrays. So this figure here on the right basically represents a spatially fed array where you have a feeding or focal source. You have the antenna array itself, which receives the radiation, does some kind of phase shifting, which can be fixed, switchable, or tunable. But normally it's done with just simple switches. That's the more standard implementation. And then it's either re-radiated on the other side of the surface, or it has a ground plane and it's reflected back to the same side where the focal source is. So there are these reflective and transmissive approaches. This Kymeta-based implementation, it's a company that has a product in the market, mainly targeting the satellite market. Also, Greener Wave is another company with a similar product in the market. So these kind of surfaces, basically they work by providing a phase shift to the radiation, to the incoming wave. So an incident wave will be affected by a certain phase shift, either in, as I said, in transmit or in reflect, or both. It can be in both. So simultaneously transmitting and reflective. Typically, these will use PIN diodes or varactor diodes. So PIN diode will be just an on-off, while a varactor will provide a continuous tunability. But of course, there are problems in these different implementations, and advantages and disadvantages. But basically, the collective programming of these diodes among all the unit cells will provide the beamforming that you need. In particular, switch-based cells, so using switches such as PIN diodes, so on-off, let's say, enable, let's say, wideband, low complexity of biocircuits and moderate quantization loss. Typical RIS, so let's call it RIS, will have between 40–50% of efficiency in a good condition. Of course, in certain scenarios it can decrease to 25% if you are playing with more low TRL technologies. So this tunability of the phase can be either continuous or discrete. Basically, in a continuous tunability, if you are able to in each unit cell to tune the phase continuously or more or less continuously, you will have this kind of phase pattern in the race, so this kind of circular phase pattern if it is illuminated in the near field. If you have only a single bit control, so this continuous, let's say, color grading will become just 2 colors, so you have just 1 bit, so 2 levels. And basically the difference between a continuous beam, as you can see here, and the 1 bit implementation is that the 1 bit will have a phantom beam, let's say. So if you steer to 30 degrees, you have a minus 30 degrees phantom beam. If you increase the number of bits, for example 2 bits, you decrease this already significantly. However, let's say this is what you get in the far field. So far field, you have this kind of strip-like phase pattern. If you illuminate it in the near field, you will get a more or less similar to what you get with the continuous, even with 1 bit. So because this, let's say this randomness that the near field provides, or this circularity of the pattern removes this this effect. So this, and then this figure here on the top right allows you to see what is the difference in aperture efficiency calculated between 3 bits, 2 bits, and 1 bit, and even the perfect one. So in terms of applications, RISEs have been in the state of the art for quite some years now. I would say that one of the most important applications is this coverage extension, where you take advantage of the RISE to reflect your signal to go around an obstacle that would block your line of sight. So you have 2 examples here, in indoor, in outdoor. Then another very important application is this RISE-enabled sensing, where you can take advantage of the RISE phase profile control to do, for example, poster recognition. You can see here in this paper, to do end gesture recognition. We have actually also published, or actually we are in the process of publishing a paper also on this end gesture recognition. So these applications in the sensing domain are really interesting as well. So then the question now, how to go up in frequency, because for the sensing, so when I show you this sensing, you have, let's say, the sensing resolution will always be connected with the wavelength. So if you are able to go up in frequency, you will be able to do a more accurate sensing, either for the gestures or for posters or whatever it is that we are interested in our application. So in the TerraMeta project, we are specifically interested in going up in frequency to enable these RISEs to work in the sub-terahertz region between 140 and 300. So how to go up in frequency, avoiding the energy scale up? It's the scale up in energy. If you go up in frequencies, as you reduce the wavelength, you will have many more elements in your RISE, and if each element consumes a lot of power, or even if it's a small amount of power, but multiplying this by thousands of elements, you rapidly scale this up. So what are the problems in going up in frequency? So this is, for example, a typical unit cell where you would use diodes, like pin diodes. But to use in sub-terahertz, the traditional packaging of pin diodes will not allow you to do it. And also pin diodes, for example, consume a lot of power, so cannot be you cannot integrate them, for example, with CMOS. They are based on different technologies. So, for example, an advanced integration with CMOS could be a solution for a sub-terahertz freeze, like you see here in this work on the right, where you use, for example, CMOS-based transistors to control each unit cell. And in this case, this is a work at 300 gigahertz from an American university. So what we are doing in the TerraMeta project, which deals mainly with these RISEs for sub-terahertz communications, it's to investigate different reconfigurable hardware technologies, so including CMOS, gallium nitride, 2D materials, and microfluidics, specifically with a strong focus on the D band, so 140 gigahertz, but also with some work as well at 300 gigahertz, and with a focus on these use cases that you see here. So a telecom scenario where you can take advantage of the RIS to steer radiation between base stations and mobile terminals, or in a factory floor environment, which I think it's actually the main use case in TerraMeta, looking at this industrial edge environment where you have mobile robots or these mobile packaging and assembly drones in your factory environment, which will connect through a RIS, so to an edge server, or base station. So the idea is that in this factory environment you have a lot of obstacles, and by deploying these RISes on the environment you would be able to go around these obstacles and relay the, let's say, for example, camera sensing data, LiDAR data from these robots. So since the focus of the project on, let's say, from the hardware perspective is mainly on these reconfigurable technologies, let's look at how they compare. So these are, let's say, the traditional technologies: PIN diodes, varactors, MEMS, liquid crystals, microfluidic, and now in TerraMeta we added these two technologies, phase change materials and MEMS resistors. What is the difference in this technology is that they are non-volatile, so this last line here, which means since they are non-volatile, they are able to not spend power when you change the state. So in a PIN diode, when you change the state, for example, and you turn on the PIN diode, it will consume a few milliwatts of power. In the off state it doesn't, but in the on state it does. With a PCM or MEMS resistor, you just consume to change state. Then after you change, it remains powerless. So these are very interesting technologies, and we are investigating both of them. So actually TerraMeta is looking not only at MEMS resistors and PCM and phase change material, but also microfluidic and CMOS-based switches. And you see here some of the advantages and disadvantages or challenges of all of these technologies. The biggest problem right now, or challenge, with MEMS resistors and phase change material is the low TRL and the difficulty in integrating them in the unit cells, as I will describe now. So this is one of the implementations done in the TerraMeta project with the phase change material specifically integrated in a 140 gigahertz unit cell. So this PCM is in practice a germanium telluride switch that can transition in nanoseconds from one state to the other through a thermal pulse. It can be with an optical actuation, for example. So given that this is a nanoscale device, we are able to integrate it with very small unit cells, so it's very good to integrate, for example, in the D-band, which is our current work. And you see here in simulation the viability of the beam steering. The other one, phase MEMS resistor, is one that in STEC is particularly pushing. And as you see here in the implementation of a 30 GHz unit cell as well as a 140 GHz unit cell. And you see here how, let's say, how you can set and reset the device using two different voltages, either a positive or a negative, or two ranges of voltages. But basically, after you change the state, you don't consume more current. And you see here that we are using fused silica substrate because we need the substrate to be completely flat to deposit this device. You see here some recent results on a RIS control using this 140 GHz unit cell based on the memristor. So going now into the last part of the presentation, which is now let's think about how could we approach a fully printed RIS that would enable a sustainable large-scale deployment. For a sustainable large-scale deployment, so thinking of different surfaces and environments, such as in building windows, facades, building roofs, there are few aspects that are interesting to look at. Now, mainly thinking not only about the power consumption, but also about the environmental impact. So in a RIS, you will have substrates, conductors, and within the conductors, it's important that if you can make the RIS transparent, for example, you could make RISs installed in solar panels, for example, so you could still have the light going through the RIS, but at the same time, you would have this functionality in your environment, such as sensing and signal relaying. And the last one is the electronics and reconfigurability that I was just talking about now, that we are interested in ways that allow you not to spend power after you change the state, so these non-volatile technologies. So in the Super IoT project, so in ESTEC is also involved, one of the demonstrators is actually this large area IoT node repeater. So this is basically a RIS that we are investigating how to make it more sustainable from the implementation point of view. So one possibility that we have investigated is this metal mesh-based RIS, where instead of having a continuous conductor, you could have this metal mesh, either this 2D mesh or 1D mesh that you can see here. So here you see the equations for the optical transparency, which is basically the covered area over the covered and plus uncovered area. And you see here a possible implementation of a unit cell, in this case using a varactor diode. Actually, this is an implementation that we were looking for to avoid any bias between the top and bottom substrate to facilitate its full printability. You can see here on the right the sheet resistance of this metal mesh as a function of transparency. So as long as we are below 1 ohm per square, in principle, we can have very high transparency, and in principle it will give you good performance of your RIS. So we are still investigating this, and here you can see the reflection coefficient as a function of the capacitance of the varactor. So some preliminary results for you to see. Actually, you see some far-field phase profile patterns. You see these stripe-like patterns for different beam steering angles between 10 and 40 degrees, and these are, just for now, these are simulation results. Although we will look for to make an implementation of this metal mesh-based RIS in the near future. Another approach is that I would like to present to you, and I know I'm running out of time, so I'll try to finish soon, is this fully printed RIS based on graphene. So graphene is a 2D material based on carbon atoms, and here we have we proposed a unit cell based on a graphene sandwich structure, where you have two graphene layers, where you are able, by applying a voltage between these two graphene layers, which is equivalent to changing the chemical potential of the graphene, we are able to control the reflection coefficient of a unit cell. In this case, using standard RF substrates. So actually you can see here some simulation results also of beam steering between -60 and +60, which also show the viability of this graphene-based implementation. But so far we also don't have an experimental realization of this yet, but we also are looking forward to it in the near future. Finally, in order to finish with something interesting, what about to achieve a fully printed RIS? We would also, for example, need, if we want to do a switch, integrate a switch in the RIS, and since we want a switch that does not consume power, as an alternative to this graphene-based implementation, we could have a fully printed memristor. Actually, memristors can be produced by Solution, and the memristors that we've been using with the Nova University in Lisbon are based on this MOS2 solution. So, and there is a trade-off here between, let's say, clean room processing and ultra-precise 3D printing. The images that you see here are actually recent results of ultra-precise 3D printing of memristors. Actually, on the left image, you see some cracks. So for you to see that we are still investigating very basic problems on how to deposit these memristor structures by full printing, okay? And also a glass substrate is required, which can be acceptable, let's say, because glass is also a sustainable substrate. And you see some recent results showing actually that these memristors work, even being fully printed. So it is also very promising. On the top right, you can also see an interconnection done with this ultra-precise 3D printing, just for you to see how interesting this technology can be. So concluding the presentation, so as I discussed, so RIS is very promising for 6G and beyond. Going up in frequency is important not only for communications bandwidth, but also for sensing, so this integrated sensing and communications. Non-volatile technologies to enable RIS at sub-terahertz with low power is a very important approach that we are approaching with memristors and phase change materials. The sustainable large-scale deployment depends on a few aspects of the RIS construction, so from substrates to conductors and possible transparent implementations, down to the electronics or reconfigurability technology. And this fully printed memristor can be a great solution for this. So the ultimate goal would be to achieve a fully printed, transparent, and energy autonomous RIS, that, for example, it could even have other functions that I didn't mention, such as energy harvesting and so on, like RF energy harvesting. So it's a very challenging topic, and we are quite deep involved in this research and would be eager to discuss with you if you have any questions. Thank you.
Thank you, Luis, for the nice presentation. So any question for Luis from the audience?
Maybe you can say to people, speak
directly. Please speak directly if you have any question. So maybe if nobody's asking, I have a question myself. Actually, I'm a bit curious on this table you put on the slide 14. So you are showing, you are comparing all these different solutions, right? These different reconfigurable techniques, and it seems this PCM and memristors are quite advantageous because of this non-volatile property, as you said, and then they require, like the memristors require very low power and so on. But it seems the switching speed is still constrained to microseconds, which is much higher than what you have with the diodes. So I wonder if this is a problem, will be limiting the applicability for some of the most advanced use cases.
Right. Actually, I don't think that is a problem because even the tracking of mobile robots, for example, in a factory environment, the speed of movement will be always in, let's say, in a few meters per second. So even with 1 millisecond update, we could be good as long as we could update a full RIS in that time frame. So if we are able to switch all the elements in parallel, which then only depends on the electronics that you have for the control. So I think and even from the implementations that I know in the market, for example, GreenerWave RIS that uses pin diodes, or actually they have now a new version. I'm not sure if it uses pin diodes anymore, but even that they can switch in 10 nanoseconds. Normally they are not worried in changing all the RIS in 10 nanoseconds. So they are normally fine with hundreds of nanoseconds to 1 millisecond, hundreds of microseconds, sorry, to 1 millisecond. So actually, I think we are good. With microfluidic techniques, it will be a bigger problem, or liquid crystals, because you will be always in the milliseconds and can be, for example, the liquid crystal based RIS that I know in the market is actually even hundreds of milliseconds. So when we stay hundreds of milliseconds, then it can be critical if you want to target a moving user or moving robot. So in that you could have a problem with this 1 microsecond. I think most use cases, I don't know of a use case that it would be critical.
Okay, I see. So especially for this tracking application, yes,
exactly,
I see.
Exactly.
Yeah.
Exactly. And even for sensing, because with sensing you will to do sensing with RIS, you don't necessarily will do beam steering. Actually, you can do like random control of the unit cells, on and off activation of groups of unit cells. So you will basically be looking into some other techniques like inverse mapping. And this microsecond actuation is quite nice because you can do many thousands of different profiles per second. So you should be able to do some real-time sensing as well with this. Yeah. Yeah.
Okay, many thanks, Luis, for the nice presentation.
My pleasure.
If there are no other questions, I think we can move forward. And the second speaker is Meng. So Meng, would you like to share your screen and start your presentation? We can see your screen.
Yeah, okay. That's good. Okay. First, I would like to thank Gilberto for organizing this webinar. My name is Meng Li. I'm coming from IMEC Leuven, and today I will represent our team from IGIT and Cloud to present our recent work for sub-terahertz transceiver architecture power analysis for the XR indoor gaming scenario. So first, I would like to make a short introduction on the 6G Shine project. The 6G Shine project aims to pioneering the main technology component for wireless in the XR subnetwork and prepare their adoption in the future 6G standards in the XR subnetwork are located at the very end of the 6G network to support highly localized and high performance connectivity. The power consumption of the sub-terahertz link is a good candidate for the INX subnetwork, which which supports short range, ultra high speed data rate when operating at the sub-terahertz frequency. The power efficiency is a key concern. Hence, in these presentations, I'm going to analyze the power energy efficiency for the sub-terahertz system for the indoor gaming application. It is one of the INX subnetwork scenario in the 6G Shine project. So the outline of my presentation, I will first introduce, make an introduction on the power model and the different beamforming architectures, and followed by the application scenarios, our methodology, the simulation results, and conclude my work. To perform the power analysis, we use our in-house developed power analysis tool. It models the powers for four main components in the communication systems: the PA, the analog front end, the digital baseband, and the power supply. The total power is calculated based on the different TX and the RX architectures, and also with the power with our years developed our number, also based on the power consumptions of the different type of PA, different component of the analog and digital digital component. The sub-terahertz frequency has very smaller wavelengths, which enable to have the compact antenna design, where the large antenna array and the beamforming architectures can increase the link budget to ensure very high data rate transmission. Hence, it is very important to analyze the power consumption and energy efficiency for different beamforming architectures. Here we focused on the our study on the fully digital, hybrid partial connected, and hybrid fully connected architecture in our study. The architecture balance digital baseband complexity and analog front-end complexity. And we will break down their characters and power requirement. We will make a breakdown analysis on their different characteristics. So in the fully digital architectures, each antenna element has a dedicated analog radio and the PA. The power model is I will need to show my I couldn't.
We can see your mouse. We can
you
see
can
the,
see.
the point,
You can see. Okay, that's
anyways,
good. Okay. So the for the fully digital beamforming architectures, and we can model the power model can be written in this equation. So for each So for these fully digital architectures, it is for each antennas, it's linked to a dedicated PA and on analog strings. So it is complex in the digital domain, and in the hybrid partial connected architectures, it reduces the digital baseband complexity compared to the fully digital. It requires less ADC and mixers, while it introduces the power consumption for the phase shifter in the analog domain. And in the hybrid fully connected architectures, all antennas are connected to all analog radios using a fully connected pre-coding network. It allows more complexity beamforming compared to the hybrid partial connected architectures, while it increases a little bit analog front-end complexity due to the fully connected network. And for each beamforming architectures, their power model has been listed here with the different equations, and you can see the difference. Then I will introduce our application scenarios. To carry out our study, we focus on the indoor gaming VR, indoor gaming scenario where multiple users are equipped with the head-mounted device, which demanding high-quality video transmission. The scenario are illustrated in these figures. The games are obtained from the cloud server, which is preloaded in the edge cloud, and the access point is located at the top center of the room, serving two different users who are equipped with the head-mounted device in the indoor environment. And we assume in this INX subnetwork cell, we use the sub-terahertz link and with a line of sight link. And the link between the access point and the users need to be reliable and with very high throughput and with efficient and power efficient, especially for the users with head-mounted device, which has a battery supply. We carry out our studies into two phases. In the first phase, we only focus on the power analysis for the access point, and in this study, we will study the impact of the impact of the energy efficiency for different bandwidths, beamforming architecture, and the different technology node. And in the second phase, in the second phase, we do joint optimization for the system, and not only considering the access point, but we also taking into account the power consumption of the users with the head-mounted device. And to simplify the analysis, we will fix our analysis in the second phase for the fix our beamforming architectures with fully digital, and also fix our technology node at 28 nanometers for the digital domain. And because we're introducing the receiver with the head-mounted device, then we also we introduce more system parameters like the video resolution and the codec compression rate, and all those two parameters will impact on the throughput requirement for the whole system. Okay, now let's take a closer look at the technology used, at the methodology used in our study. We start with the key parameters that will influence the system performance, the bandwidth, the channel realization, which models the geometric, the spatial characteristic of the TX and RX, and different beamforming architectures, and the different numbers of antennas at the TX and RX. And using those inputs, we can calculate the system's throughput. So different channel realization, geometric parameters, beamforming architectures, and the number of antennas at the TX and RX will results in different SINR, and at the with the gaming communication performance requirement, such as we set our target bit error rate as 10-5, then the SINR will determine the selected modulation modes. And once we know the modulation modes and also with the bandwidth, then we calculate the throughput. And on the power side, once the beamforming architectures with the different settings of antennas are determined, and with the knowledge of power consumption of the both power consumption of the analog and digital components, and also the flops in the in the digital size, and we can calculate the power consumptions of the systems. And finally, we can combine the calculation to evaluate how the beamforming architectures and bandwidths and the size of antennas can influence our systems throughput and power consumption. Now let's look at our results. Here is the simulation parameters used in our phase 1 study. So first is for the geometric setup for the channel. So we assume the access point is fixed at the ceiling of the room and with a height of 5 meters, and the user's height is uniform distributed from 1.5 and 1.8 meters, and we have discrete discrete angles of this user locations in both directions, and the carrier frequency we assume is 140 gigahertz. The bandwidth we considered for this phase is 1, 2, and 4 gigahertz, and we target throughput is for the average throughput is 1 gigabit per second for the downlink. Target system performance is the bit error rate 10 minus 5, and we assume number of simultaneous active users in the same band is 2. We use the waveforms. We use the waveform we use in our simulation is for the 11AD standard single carrier and the OFDM. We assume the channel between the user and the between the AP and users is a line of sight. And here are all the here are all the parameters linked to the base for the baseband architectures. We assume the maximum PA output is 14 dBm, and the maximum size of the array is from 4 to 32. And for each numbers here listed the size of the antenna array. And at the user side, we assume the user have this 2 by 2 antenna size. And now let's look at the result and conclusion. So first, on these figures, it shows the number of TX antennas versus the average throughput for user, and under different system bandwidths and for different beamforming architecture. And in general, we can say for fixed architectures, and the throughput increase linearly with the bandwidth, and for fixed bandwidth, the fully digital and the HFC architectures support the same throughput, which both benefit from the spatial diversity. And the hybrid partial connected beamforming architecture, it cannot achieve the same EIRP as the HFC and FD. Hence, it leads to a little bit lower throughput. And and then let's look at the result for the energy efficiency. So this figure shows the number of TX antenna versus the energy efficiency. for different bandwidths and for different beamforming architectures with the technology node at 7 nanometers. And the bottom figures show the results with the same setting, but at the technology node at 2 nanometers. And then we can get the conclusion, we can, from these simulation results, and we can get the conclusion. So for fixed architectures and for fixed technology node, the wideband system provide better energy efficiency. And if we compare the beamforming architectures for the HFC versus HPC at given bandwidth and given technology, the smaller for the smaller antenna array, the HFC beamforming architecture is more energy efficient than HPC. But for the large antenna array, the HFC architectures outperforms the HFC due to the reduced splitter loss. And for the technology impact, from 7 nanometers to 2 nanometers, and we can see the gap between the fully digital beamforming architecture and the HPC and HFC decreases because the digital circuits benefit more from the scaling than the analog circuits. And for the fully digital beamforming architectures, it even can outperform the HFC and HPC at very small antenna array at the at 1 gigahertz bandwidth in our simulation results. Now let's look at the simulation parameters used in the second phase of our study. So compared to the phase 1, we keep most of the simulation parameters, but we increase the numbers of antennas at the transmitter side and also at the receiver side. And besides this, we also introduced 2 different parameters, which are the video resolution at the head-mounted device and also the codec compression rate. And in this table, it listed the different throughput requirement for the different combination of different video resolution and different compression rate. And because of the limited time, I will just show our results for those 2 cases. So with 4K state-of-art 4K video resolution and uncompressed codec rate and with ultra low latency compression, the compression rate is 5 to 1. Now let's look at the simulation results. So this figure shows the different antennas at the receiver side versus average throughput per user for different cases, which the receiver side were configured with different antenna, different number of antennas, and I plotted the purple line, which is the throughput requirement for the 4K video uncompression codec uncompression case, the throughput requirement. And I also listed the throughput requirement for this 4K video and ultra low latency compression rate. And all the TX and RX architectures with different antennas, the configuration point above this requirement, they can satisfy the system requirement in throughput, and we will we can calculate the powers with these settings and used in our power optimizations later. And in these slides, it represents the simulation results for energy efficiency optimization for this 4K VR scenario, and using fully digital beamforming architectures at 28 nanometers. The objective functions for this joint co-optimization is listed here. Here, the beta is the tuning parameters, which is the tuning parameters. So once the beta is equal to 1, then the system is optimized for the receiver side, and when the beta is equal to zeros, and the optimization is tuning for the optimization for the TX. And if we choose beta equals to 0.5, then it is optimization as the whole overall systems taking into account both TX and RX. And the figures on the top right, it listed the average powers for the TX and RX with a different configuration of antenna size, which satisfies the throughput requirement. And this table shows three special cases. So we can say if we only want to optimize this power consumptions for the TX, and then we get this result. We get this result. Then we get this result. So the TX, the minimum power consumptions at TS, it could be at 4.7 watt, but with a relatively high power consumption at the RX. And on the other way around, if we optimize the power consumptions for the RX, and the minimum RX powers can only consume 0.31 watt, but it will end up with a relatively high power consumption at the TX, and it's shown this point. And these figures also shows the power breakdown for the both TX and RX for the three special case. And then I will conclude my talk. The power and energy efficiency for different beamforming architecture has been studied in the INX subnetwork using sub-terahertz link for indoor VR gaming scenario. During our study, we find out the HFC is more energy efficient with smaller and antenna configuration, while the HFC beamforming architecture is more energy efficient with large antenna configuration. So fully digital beamforming architectures improve the most with technology scaling, and it is the most efficient for the small antenna array at low bandwidth. We analyze the trade-off between the average power consumption of access point and head-mounted device for different VR realization, resolution, compression rate, and we demonstrate the joint optimization for the access point and head-mount device with different number of antenna configuration, and we show that the average access AP power consumption can be tens of milliwatt once the communication system is optimized for for the access point. And while the average head-mounted device power consumption can be also a few of milliwatt when the communication system is optimized for the head-mounted device power consumption. And thanks.
Thank you.
That's
Thanks.
end my presentation.
Thanks, Meng, for the nice presentation. Any
Nice
comment or
reference.
question to Meng? So maybe we're running a little bit late, so just maybe a quick question myself. You are showing all these different components, right, that contribute to the cumulative power consumption, right, of all these different transceiver architecture. So what is the, let's say, the bottleneck? What is the main, let's say, component to the overall consumption here? So what is that we should optimize more? Yes.
There are, the only difference is that you say for this, I noticed for the phase shifters, it is only at the, we do not have these ones in the fully digital architecture because that's in the digital domain, but in the HPC and HFC, they are, these are in the analog domain. And the difference between the HPC and HFCs is the numbers of this phase array. So in this case, here, so in this case, is n times the p phase array, but in the HFC, it is n times k type. N times the k, and the most I think this is the major difference between HPC and HFC.
Okay, so this brings to the fact that for low number of antennas, one architecture might be more advantageous than the other as well, right?
Yes, that's the major difference for the power. Yes.
I see. Okay, thank you, Meng, again for the nice presentations. If there are no other questions, then we can move to the last presentation by Yasser. So Yasser, would you like to share your screen?
Yes, thank you. So can you see my screen?
Yes.
Okay. Good morning, everyone. Thank you for attending to this webinar. I'd like to thank the organizers, especially Gilberto, for arranging this opportunity. I'm Yasser Karagöz from KU Leuven University. I will share our work titled Biased FSK Modulation for Simultaneous Wireless Information and Power Transfer, conducted in collaboration with Professor Sophie Poulain and Professor Dominique Schroers at KU Leuven. So today's presentation will cover 4 key points: an introduction to the motivation of the work and the challenges of IoT nodes and the biased FSK modulation, and the conclusion. So why do we need sensor nodes? IoT connects devices into a network to collect and exchange data, enabling smart decisions and improved efficiency. Examples include smart homes for automation, wearables for health insights, smart grids for efficient energy use, industrial sensors for predictive maintenance, and precision agriculture for better yields. So sensor nodes power these innovations, making smarter, sustainable technologies possible. So let's look at a real-world example of IoT in action, smart agriculture. This approach leverages technology to optimize farming practices. Environmental control units regulate factors like temperature, humidity, and nutrient delivery, ensuring plants grow in ideal conditions. Sensor devices can continuously monitor critical metrics such as soil moisture and plant health. The collected data is then sent to a sensor node, as you can see in the figure. here. Here. So sensor nodes through a cloud, which communicates with the central base station. The base station acts as the system's brain, analyzing the data and making decisions to improve crop yield, reduce waste, and ensure sustainable farming practices. So powering sensor nodes present a significant challenge. The primary issue lies in reliance on battery power. Batteries have limited lifespan, requiring frequent replacements for recharging, which increases maintenance efforts. Additionally, this reliance has a notable environmental impact, contributing to waste and resource consumption. Addressing these challenges is critical to create sustainable and efficient IoT systems. Sensor nodes face even greater challenges when deployed in diverse and demanding environments. Many nodes operate in remote or inaccessible areas, from freezing Arctic landscapes to extreme terrains like the Martian surface, for example, shown here. These locations often lack infrastructure, experience extreme weather conditions, and make maintenance nearly impossible. Such harsh environments not only test the durability of sensor nodes, but also accelerate battery depletion, jeopardizing consistent and reliable operation. So simultaneous wireless information and power transfer, or SWIFT, is an interesting approach that combines energy harvesting with data transmission in a single process. Here's how it works. We begin with a multi-tone signal. As you can see in the left-hand side picture, multi-tone signal, which combines multiple frequencies. This signal has a high peak to average power ratio, PAPR, making it efficient for energy harvesting. As the multi-tone signal passes through a nonlinear device like diode, it generates a DC output, which we use to harvest energy. Simultaneously, the modulated input, represented by a two-tone signal, F2 minus F1, this difference between the two frequencies becomes the received data. So this method allows us to power devices while transmitting data, ideal for applications where using or replacing batteries is not a practical. It's a dual-purpose solution for wireless systems. So this slide introduces our biased FSK modulation scheme for SWIFT. Unlike traditional FSK, which uses equal power across tones, our approach optimizes the side tones, the power of the side tones to be proportional to the central tone's power. The central tone remains constant while the side tones are symmetrically positioned for efficient data encoding. Biased FSK also leverages the rectifier. As you can see here, rectifier has a low-pass frequency-dependent response for two decoding options. One is high attenuation for simpler, energy-efficient decoding using comparators by placing this difference inside the band of the rectifier or one of them outside the band of the rectifier, and low attenuation for advanced FFT-based decoding when more power is available on the node side. This design ensures efficient and flexible demodulation for SWIFT. So this slide demonstrates the effectiveness of our biased FSK modulation method by optimizing the power ratio of the tones. As you can see, the left-hand side, the blue is a biased FSK and the red color curve is a conventional FSK. We achieved a 6.2% reduction in total harmonic distortion compared to traditional equal amplitude FSK, frequency shift keying. The left graph shows how our approach results in a smoother time domain signal, while the right graph highlights the reduction in unwanted frequency components. In simpler terms, biased FSK produces cleaner signals with less interference, improving the reliability of wireless power and data transfer. And here, this slide showcases our experimental setup for over-the-air testing of the SWIP system. We designed this to evaluate wireless power transfer and data transfer performance over a 1.3 meter distance using a frequency shift keying signal. The key components include a transmitter antenna, a horn antenna, and the power amplifier to compensate for the freeze loss, and the receiving antenna, another horn antenna connected to the node. And this slide shows the coherent detection of biased FSK. As you can see here is the data. On the right-hand side, you see the binary data that we transferred over the air, and this is, the second one is the transmitted waveform that the frequencies F1 and F2 are 200 kilohertz and 100 kilohertz. The distance to the carrier frequency, and the third curve shows the received signal, which is the rectifier's output. It contains both frequency shift keying, as you can see, the 100 and 200 kilohertz, plus the DC energy, and you can see its spectrum. So in this method, we don't have any distortion, and we can just, with FFT approaches, we can extract our data. But this requires more energy on the node side. So if we have energy and we want to transmit lots of data, high data rate signal, this is a good approach with more accuracy. But on the other hand, if we don't have enough data, the biased FSK modulation gives us this non-coherent detection, a simpler, more energy efficient option, which is ideal for low complexity systems. As you can see in the graph, we have a 10 megahertz for F1 and F2 is a 100 kilohertz. So because 10 megahertz is out of the rectifier band, we deliberately choose to be out of the rectifier band. So it is suppressed. So only we can see the 100 kilohertz. So by this way, we can just use a simple comparator on the node side to detect our transmitted data. So this requires very low energy. So when we don't have enough energy on the batteryless node, so we can use this approach. And here we see the bit rate performance at various SNR levels. At 10 dB SNR, biased FSK achieved a 5.5 times lower bit rate compared to conventional FSK frequency shifting. This demonstrates better performance at lower SNR levels. However, as SNR increases, the bit error rate for both configurations becomes comparable. At extreme SNR values, bit error rate increases due to noise at low SNR and nonlinearity distortion at high SNR values. And this slide summarizes key SWIP modulation techniques and their strengths and challenges. ASK is a simple and energy efficient for basic systems, but struggles with complexity and distortions because it's dependent on the amplitude, and it generates many distortions for a nonlinear device like a diode. And on the other hand, PSK, phase shift keying, is a great for high data rates, but requires complex phase synchronization. FSK stands out for its simplicity and noise resistance, making it ideal for low power batteryless devices. And the biased FSK method improves on this by reducing signal distortion by over 6% and optimizing energy efficiency. It's a strong option for efficient and sustainable SWIP systems. To wrap up, here are the key takeaways and our future directions. First, our biased FSK modulation method enhances sweep performance by balancing power across tones, improving energy efficiency and reliability. Additionally, the adaptive reception strategy ensures the system can handle a variety of energy requirements on the node side. Looking ahead, we aim to integrate eco-friendly materials to reduce the environmental impact of sweep systems. We're also exploring the use of machine learning to optimize system performance in real time, making these systems even smarter and more efficient in practical applications. And any questions?
Thank you. Thanks, Yasser, for the nice presentation. Any comment or question for Yasser? Seems not. So maybe just a question myself. So
Yes.
in practice, what is actually how much energy are you able to harvest by this modulation? So compared to the other ones that you have listed, like AESK and so on.
So
how efficient it is?
Yeah. From the modulation energy harvesting point of view, they are mostly FSK, because FSK doesn't change the envelope. And for energy harvesting, for example, ASK, when you go to 0, the envelope is 0, so there will be no energy for harvesting. So FSK and PSK have similar and better energy harvesting than ASK. But yeah, for energy harvesting, PSK and FSK are good options. But on the other hand, as I said, for information, because for rectifier, it's important that you don't see lots of fluctuations on the envelope. And FSK doesn't show any fluctuations on the envelope, only you can see the frequencies changing. So it's also doesn't affect the energy harvesting.
So, but you're biased FSK, I understand.
Yes.
So you have this combination of tones that create a large PAPR, right?
Yes. That one improves the energy efficiency, because when you have high PAPR, you can turn on the diode fast and it works in more linear region, so you can have higher efficiency in comparison to FSK. Also, we need to find the optimum power ratio, because as you can see, when you have equal amplitude FSK, you generate some frequency components that makes your receive signal more distorted and difficult to retrieve that data.
I see. Okay, sounds interesting. Yeah, interesting approach. It's like this modulation is something, let's say you generated yourself in the project.
Yes.
Rendered yourself. Okay.
Yeah. Part of our work in KU Leuven is to design signals that are more compatible with the diode. We don't have amplifiers like the low noise amplifier or power amplifiers, which are working in the linear region. So we need to take into account the rectifiers, its own performance, because we don't use any bias. It's kind of without bias. So we need to to create that bias by our transmitted signal for the diodes.
I see. Okay, thank you. Yes, yes, please.
Excuse me, may I ask something?
Sure.
Maybe you have already answered that, but what about this 0.5 ratio between K1 and K3? Is it the optimal one? K2, yes. Is it the optimal one, or is it just because we want a half? Have you ever tried 0.2, for example?
Yes, we tried, and actually I have a journal paper you can see here. So we tried different ratios. At 0.5 ratio, you have highest energy conversion efficiency. At the same time, it doesn't distort the data, because we have two functions here. One is the energy harvesting, we need to find a very good point for energy harvesting to have high energy conversion efficiency. At the same time, we don't want to distort our data. So the blue color, which is a 0.5, has the highest energy efficiency. At the same time, it doesn't distort your data.
Okay.
I hope
Okay.
I was able
Thank
to
you.
answer your question.
Yeah.
Thanks. Any other comment or question for Yasser? If not, I think we can wrap up. So I would like to thank again all the speakers and the audience for joining this webinar. Hopefully this is the first one of a series of webinar that will continue starting from New Year. So many thanks for joining, and wish you a nice afternoon and a nice weekend when time comes. Thanks.
Thank you. Bye.
Thanks. Bye.
Bye.